Hello students, I hope your weekend is going well. These are your notes for Tuesday, October the 15th. We're going to be beginning Unit 3. Unit 3 is going to deal with a bunch of stuff that will hopefully be remedial for you. We're going to talk about equations of lines and slope-intercept form, but then we'll get into some more advanced formats for equations, such as standard form and point-slope form, and eventually get into inequalities, and then of course word problems dealing with linear equalities and linear inequalities, and that's what Unit 3 is going to be doing over the next few weeks. So let's get started. Your objective for today, or Tuesday rather, is the student will discover the process and applications of the slope formula. Again, the date for Tuesday's class, I believe, is Tuesday, October the 15th. So record your objective and your date, and then press pause anytime you need more time, and then hit play when you're ready to move forward. All right, a little bit of review here from Once Upon a Time. Slope-intercept form, of course, is y equals mx plus b, and in slope-intercept form, a line needs two things in order to do what it does. Okay, and with those things are plugged into our equation, m and b. Okay, and those two things tell the line these two things. It gives the line somewhere to start, and then it gives the line somewhere to go. Now, somewhere to start, that's typically where we obviously begin our line, and that is the y-intercept. It tells our line where to cross the y-axis. Everything else that the line needs, it gets solely from the slope value. Okay, so somewhere to start is the y-intercept, but somewhere to go is the slope value of the line. Okay, we're going to start off by examining the slope, and in the next few days we will get into how to calculate the y-axis intercept. But the slope is going to tell the line as you leave the y-intercept, what direction do you go, how fast do you go, okay, upwards or downwards, or quickly or slowly, or horizontally or vertically. All of that comes from the slope value. Okay, now, one of the things that I'm sure you're probably familiar with is that there's a lot of different ways that a question can come out and ask you or speak to you about the slope value of a line. And unfortunately, we need to be familiar with all of them, and I may actually have a couple that you've never seen before. Okay, but let's start with the basics. First off, obviously, they could come out and say slope. However, I think that's a little bit unrealistic at this stage of the game. If we were in pre-algebra or maybe even algebra 1, they might ask for slope. But these days, with us being in algebra 2, they're probably going to use something a little bit more technical than just the word slope. From time to time, you will hear an algebraic problem refer to the m value of a problem, in which case that m is referring to, as in y equals mx plus b, it's asking for slope. Okay, but again, that may be a little bit too low level, so I doubt they'll ask for it that way either. Okay. One way that you can probably be certain that they're not going to ask you is rise over run. Okay, the people that write the ACT and the SAT and any standardized test, they understand that this is the way that slope is taught to you in junior high, so they understand that all of you understand rise over run. Okay, so they're not going to use that language on us. Probably going to be something more complicated. From time to time, you will see a question actually use the slope calculation formula exactly like this. Okay, this is how the slope value is calculated based upon the coordinates of 2 points on the line. We have 2 points, which we're going to see are x1, comma y1, and x2, comma y2. And using those 4 values, the 2 abscisses and the 2 ordinates, we can plug into this formula for y2 minus y1 over x2 minus x1, and it will tell us exactly what is going on with the slope of the line. Another thing they can say is they can put it in more plain language. Okay, problem might actually refer to the change in y over the change in x. Well, if you think about what this says, this is, in plain English, what the slope formula from number 4 is asking about or referring to. Change in y. That is the difference of the y values as you move from one point to the other point. That's exactly what the numerator in number 4 is doing. Okay, a problem, and then in the denominator, or the rest of the sentence rather, okay, over change in x. Change in x, it's measuring how do the x values change as you move from one point to the other. That's what the denominator is talking about there. Okay, here's a new one that you may or may not be familiar with. Okay, they might use delta. Okay, this says delta y over delta x. And as you go higher and higher in mathematics, and you're probably getting to some of this in your science classes as well, you will start to see the Greek alphabet start to make an appearance. Okay, this little triangle guy is one of the lowercase Greek letters, which is delta. Okay, and these Greek alphabet letters have mathematical meanings assigned to them, and the meaning assigned to this little triangle delta, okay, delta is change. Okay, so this actually says change in y over change in x. Well, look back at the language on number 5. Exactly the same, change in y over change in x, and that's exactly what number 4 says in formula form as well. So 4, 5, and 6 are all identical, even though they look very different. And the language of choice here the last few years has been this one. Problems have been very frequently referring to rate of change. And rate of change is just a fancy way of asking for the slope. Okay, so a lot of synonyms there, a lot of ways we're going to need to know it, and unfortunately we have very little way of knowing how they will ask the question. So we need to know all of their little synonyms just in case any of them happen to show up. Okay, now the basics of the slope value. Slope is a fraction, whether it is written as one or not. As you should be getting familiar with the old complaint where students said, "I don't like fractions." Well, we should pretty much be at the point where we now understand everything is a fraction. Okay, so just like any other fraction, the numerator means something to the problem and the denominator means something else to the problem, and a lot can be told just from observing the slope value in the equation of a line. Okay, so as you can probably have seen this year, we're really valuing understanding what those numbers in the equations actually mean. Okay, well, slope is a value that we can understand if we simply know how to read it. Okay, if your slope value is a positive number, then this will mean that your line is moving upwards as you look from left to right in the graph. And that's how we read our graphs, is from left to right. Okay, so a positive value means the graph will climb as you read it from left to right. A positive rise value will cause the graph to go up. And it can also be a negative value, in which case the line will move downward as you read from left to right in the graph. Okay, so a negative slope means you have not a climbing graph, but a falling rise. Okay, so it will drop down and then run left to right. Okay. Now, it's possible that our slope's value itself could be larger than 1. Now from the parent function, y equals x, okay, 1 is the parent function's slope value. So as you get a larger value than that, that means that you are rising faster than you are running. That will cause the line to move upward or downward more quickly. Okay, so that should be sound the same as when we talked about amplitude with our parent functions. Cause the graph, the bigger number, the more the number gets bigger than 1, okay, the more hurry the graph is in. And similarly, we could have a value that is smaller than 1. That will mean that your rise is not quite as big as your run. It will be running faster than it rises. That's going to cause the graph to move upward or downward more slowly. Okay, same as we've been talking about with our parent functions. No difference here. Okay, it is possible that your slope value might indicate that the line will run but refuses to rise. That will put a 0 in your numerator and then some other number in the denominator. Well, a fraction that has a 0 in the numerator has an overall value of 0. Okay, so that will be a horizontal line. It is running, but not rising. Now, back in the day when you went through Algebra 1 or pre-algebra, you might have had a teacher that taught you no slope on a horizontal line. They were not incorrect for doing that, but here in the last few years, the powers that be have decided that no slope is a bad term, and they instead want us to know zero slope. Okay, so if you learn no slope, you're going to need to unmemorize that and learn it instead as zero slope. On the flip side of that, we could have a slope that indicates that the line will rise but refuse to run. That means we will have a numerator, a number in our numerator, but our denominator will be a 0. And as you should recall from our discussion on vertical asymptotes, zeros in the denominator cause the fraction to fail, and we have an undefined situation there. That means that our graph is vertical. Okay, vertical line. So the slope of a vertical line will be called undefined, or from time to time you will see the infinity symbol. Okay, let's look at an example here real quick. What is the slope of the line connecting the points -2, 3 and 6, 7? Now I'm going to give you a strategy here that you're probably not going to like, but we're going to do it anyway. These formulas that have all of the x1s and x2s and y1s and y2s, okay, and by these formulas I'm talking about slope like we're doing today, and also the distance formula and the midpoint formula and the point slope formula and all that stuff. I want us to get into the habit of labeling our coordinates. Okay, so we're going to need these two coordinates, these two ordered pairs, in order to plug into the slope formula. We're going to label them. So I actually want you to physically write down on your paper when it comes time to work a problem that needs these values. I want you to write down, label one of the points, x1, y1, and label the other one, x2, y2. How do you know which one is point 1 and which one is point 2? It does not matter. We will all get to the same answer as long as we don't make any mistakes, but I want you to actually label them. The next thing I'm going to want you to do that you probably won't like either is anytime we're going to plug into a formula, I want you to write the formula down on your paper. Even if that means if we're working 10 problems and you got to write it down 10 times, then that's simply what we're going to do. And this is something that I'm going to be looking for while I'm grading papers, and I am going to deduct points for people that do not do this. Okay, our problem is we try to do too much mentally, trying to plug numbers into formulas in our heads, and unfortunately we're just not that good at it, and it's causing us to make a lot of silly mistakes. If we will label our points and write down our formula and have it all in one place, that can eliminate a lot of the silly mistakes. From here on, all we have to do is plug in our values. Okay, the formula asks for y2, which in this problem is a 7. The formula has a minus sign built into it, so pay attention to that. The formula asks for y1, which is 3. Then the formula says to divide that by x2, which is 6, minus x1, which is -2. Now, a lot of the formulas you're going to get into in Algebra 2 and higher, you're going to see a lot of subtraction inside of the formulas. So pay special close attention to all of the subtraction and negatives, and do not lose any of that stuff. That's one of the silly little mistakes that I'm referring to. Let's not lose our negatives and our subtraction signs. The numerator has 7 minus 3 in it. Obviously, that is 4. The denominator has 6 minus -2. Double negative is going to cancel each other and make it positive. So the denominator is 6 plus 2, which is 8. And with our slope fraction, we will always reduce it as far down as we can. There's no reason to turn it into a decimal point or anything like that, because the numerator means something and the denominator means something also. So we kind of need the fraction, and in this case, the fraction is positive 1/2. Now, what can you tell about this line based upon its slope? Okay, well, two things we can tell about it. First off, it is a positive value. What is that going to mean to the graph? Positive means the graph will rise as you read it from left to right. So our graph is going to be moving upwards. And 1/2 is a value that is smaller than 1. What will that mean to the graph? that will mean that the graph is not in a big hurry. It is going to be more horizontal than the parent function. So it is moving up from left to right, and it rises slowly. Now we'll look at a couple more examples in class together on Tuesday. I think you've probably got it, but we will look at a couple examples anyway. So take a moment and copy these down. You can go ahead and work them out on your paper if you feel comfortable with it. But as I said, we will go over it in class on Tuesday. And if you go ahead and do it, hopefully I'll be able to verify that you got the right answer for you on Tuesday. But what is the slope of the line connecting points -4, 7 and 0, -5? Press pause if you need more time. And then also, what is the slope of the line connecting points 3, 2 and 3, -1? Again, this should feel very much like review. Slope is not a new topic for Algebra 2. In fact, these first 3, maybe 4 days are going to feel like a whole lot of review, and then we'll get into stuff that's a little bit more challenging, but many of you may know some more of the stuff that we're going to be doing on this unit anyway. At any rate, I appreciate you finding time this weekend to take your notes. I will see you in class on Tuesday.